Good afternoon, I'm Yiwa Astle. I'm one of the data scientists from Vista Analytics. We're a consulting company that provides advanced analytics and machine learning solutions to clients in the dispute and litigation domain. The topic I'm going to talk about is an application of dynamic logistic regression with unscented common filter. It's quite a mouthful. I hope by the end of the presentation, you'll have a clear idea what the use cases. And so what is predictive coding? In litigation proceedings, each party to a case has to present documents or data records to the opposing party or regulator for your defense or claim. And suppose your company under investigation by the Department of Justice. You have to present, go through a large volume of data in order to present what is relevant to the case. And this process is normally done what is called electronic discovery or e-discovery, where you go in and identify the data sources and perform the preservation and collection. What you end up having are a massive amount of documents, millions of records. In the golden days, lawyers use manual review to go through all these documents and label them as responsive or non-responsive. In today's world, the amount of data is almost doubling every year, and the variety of data is ever increasing. So manually going through these documents to label them is simply unattainable. So here comes the application of predictive coding, which utilizes a supervised machine learning model to automatically classify a document into responsive or non-responsive. So it is essentially a text categorization model. So the standard predictive coding workflow nowadays is the active learning framework, where you start with a training set, and then your training set is repeatedly augmented by additional labeled documents. So each round, you sample additional documents, and you label them and add it to your training set. And you repeat this iteration until your model performance is stable, and then you perform the validation to generalize your model to be applied to the unlabeled population. So I said that predictive coding is very similar to text classification, but it's different in two ways. First, unlike a lot of the classification problem where you try to optimize accuracy, predictive coding try to optimize recall, the percent of responsive documents found during this review process. And the second is that unlike text classification, for example, the citation screening, Dr. Carla broadly talked about this morning, where reviewers have a very clear defined idea what they're trying to look for. In predictive coding, lawyers start with little or no, or sometimes wrong or biased understanding about the case. So the second problem actually is what we call concept drift, which means the underlying patterns in data change over time. In predictive coding, it could be that the understanding from the lawyers are evolving over time, and it could also be additional document requests that lead to previously unresponsive documents to be responsive. And it could be that development in the case that's previously unforeseen. So there's a lot of reasons going to concept drift. So what you end up having is this non-stationary label that change over time. So active learning framework allows new information to be added to your model. But the problem is if you have a large training set to start with, you simply need a lot more new data to provide this information. So this training cost is higher and higher as you accumulate more training data. So what we're proposing is to use an online learning technique that's called dynamic regression with unscented common filter. Basically, what it does is it models the weights in a logistic regression as time-varying parameters. So this captures the concept drift very well, and it works with streaming data. So in a review process, you can think of this as a streaming data as well. and it's easy to retrain and score, and then you can validate the performance. And then compared to the traditional active learning with logistic regression, it actually requires less human labeling effort, which we're going to show in the experiment. So the next few slides are on the equations, a lot of mathematics. I'm going to provide as much intuition as possible. So here the first equation is a logistic regression where you have the input vector x and you're trying to map it to the label by adjusting the set of weights. So this here is basically an optimization problem. And common filter is where you have is a recursive update solution where you have two systems. The first is kind of like your logistic regression, other than it's linear, where you have the input vector and you try to map it to the observation. And then you have a process equation, which is given the weights from the time period, last period, what's the weights, or what's the current weight. So this is where we try to model the weights of time varying parameters, try to capture the concept drift. So given to a linear system with Gaussian distribution, here's the update rule. What this says is that your current expected weights is the expected weights from the previous period plus some sort of common gain. And the common gain here is the P is the covariance matrix. So from reading this, you can see that this is some sort of uncertainty trade-off between your parameter and your observation. So an intuition will be, for example, your measurement observation system is completely unreliable. So this PYY is going to be assuming infinity. So what it says is that if your observation system is completely unreliable, then you shouldn't trust it. Your current estimation should just be your previous estimation, and any new observation does not provide any input, new information on your estimation on the weights. So because logistic regression is a nonlinear transformation, we cannot use a common filter as the update rule. What we did is use the uncentered transformation where you generate a set of sigmoid points to estimate the posterior mean and the covariance for the update. I'm going to skip this, and if you're interested, you can go to the paper for more reference. And so basically, you use the sigmoid points to estimate your covariance matrix and estimate the mean, and then you plug it into the first slide for the update. So what we did is essentially we start with a logistic regression model from the training set, and then for each subsequent newly arrived data points, we use the uncentered common filter to update the weights in logistic regression. And the data we used are a set of text documents from 20 News Group. These are pre-labeled documents with topics. It does not have a time dimension, but because review is is streaming data basically. What we did is we try to simulate a review process by dividing the documents into 7 chunks representing 7 time frames. So T0 is where we build the training set, and then each subsequent period represent a batch of review session where you perform the active learning iteration, basically review more data, add it to your training set, and rebuild the data. And to simulate concept drift, we specified a decision function, a binary decision function to represent the simulated reviewer. 2 types of concept drift were simulated. First one is concept shift, where you have a sudden shift in decision. For example, you started with all hockey documents being responsive, then at time t, your decision flipped and to be all baseball documents to be responsive. And for concept drift, instead of this sudden change in decision, now we have a gradual incremental change each period. So this 0.8 represents that 80% of hockey documents are responsive. So from this binary decision-making function, we can simulate a synthetic concept drift. So this is what we did to simulate a consecutive concept drift, and we repeated the sampling 100 times, and then we averaged the result for the comparison. So here's an overview of the experiment. From the initial training set, we built a logistic regression, and then for each subsequent period, we sample documents, additional documents, and add it to the training set to augment the training set and either rebuild or use the unscented common filter to update the model. And for each model built at the current period, we apply it to the subsequent set of documents. This is to measure how fast the model is adapting to new changes. And we measure the area under the curve for each batch's documents. And for the final set of validation, we measure recall as a function of human review effort, understanding that in predictive coding, what you're interested is to get the maximum responsive documents out of your population. And we also tested 3 ways of sampling your documents, which are random sampling and decision value sampling, and also using what is called top-ranked sampling, meaning using the most responsive documents to augment your training set. And here is the result area under the curve for each period. So the vertical panels are the number of documents sampled each batch to augment the training set. And the horizontal panels are the sampling method we used. And the red line is our benchmark, which is the conventional active learning, where you rebuild logistic regression each round. And the teal color line is what we implemented with unscented common filter. So what you observe is that after your decision-making change, your model falls into this chaos status. But with more additional documents provided, both model improved, but unscented common filter really improved at a faster rate than active learning. And this gap is even more prominent when you have a limited number of documents to use for augmenting your training set. And this chart is on recall. So the x-axis is the number of documents reviewed in validation. So here you started from, you rank basically in the validation, you rank the documents from most responsive to least responsive, and you start a review from the top to the bottom. And if you review 100% of them, then your recall is 100%. So what we're trying to see is that which algorithm perform better when the number of documents reviewed is less. So what you can see is that unscented common filter always gave a better recall, regardless the number of documents sampled and the sampling method. And this is the chart area under the curve for concept drift, where you can see that unscented common filter is picking up the new pattern at a faster rate. It always had a higher accuracy, almost always had a higher accuracy compared to the active learning framework. Well, the unscented common filter is also an active learning framework, but compared to the standard active learning framework. Here's the chart for recall. Similar pattern that we observed as in the previous scenario for concept shift, where the recall is always higher given the same number of documents reviewed, indicating that our model has better performance overall in the validation set. We also tried something called active label request. So instead of specifying the number of documents to be labeled and added to your training set, we instead specified an uncertainty cutoff for the model to actively request the label. what we found out is that the number of documents the model requested is a somewhat optimized number between the review effort and the model performance. So our conclusions are with both types of concept drift, logistic regression with unsigned common filter showed faster rate of learning new patterns. It has better overall performance in terms of accuracy and the final recall in the validation set. It also requires less labeling effort given the same amount of to achieve the same level of performance regardless sampling selection strategy. So since we submitted this paper, we actually improved our solution further by embedding in ensemble learning. Because like other online techniques, unsigned common filter have very good plasticity, but ensemble learning further improved this, the stability of our model. And with the ensemble learning, now we can have more selections on the algorithm, not just the logistic regression. We can take advantage of a variety of algorithms. And we also further tested the ensemble learning with unsigned common filter on a set of spam email data. So spam email data has natural concept drift in it because the spam fraud schemes is constantly evolving and changing, might be returning to its old scheme. So what we did is that we ran the experiment on the spam email data, and our approach again showed better result. But that's after the submission of this paper, so it's not included in this deck. And if you're interested in talking to me about our solution in predictive coding or our future work, or our company, Vista Analytics, happy to talk to you after the presentation.
More time for the question, actually. So, any questions?
What kind of features you use?
So we, just like standard NLP, trying to go back to the first slide, but just talk about it. So these are text documents, right? So we tokenize it, tried n-grams, remove stop words, some pre-processing, but it's pretty standard. We try to not to tune the parameters when we do these tests. So, and we use the same set of features for both experiments. Yeah.
Have you ever tried different word embeddings?
Different.
Word embeddings like word2vec or glove vectors?
Yes. So word2vec or glot2vec or doc2vec, these are just representation of your text data, right? I think it might improve the result further, but it's not the point of this experiment. This experiment is to try to see how do we update a model to address the problem of concept drift in predictive coding. Yes.
So I have a question. So if you, I saw you actually use like more than 200 documents, right, in your experiment, roughly, or actually more. So I'm wondering, like, you know, what time, like, is for the learning, you know, that how long, like, you run in the cloud or you run in the just a general, you know, like desktop. Regular. How long usually does it take to finish like a kind of learning process?
So.
By hour or 2 hours.
Yes. So because we repeat. We run this on a desktop,
okay.
And we repeat the experiment for 100 times, and there are different sets of sampling method and sampling size. So I don't know exactly how long does it take for one iteration, but a few minutes,
Okay.
seconds. It also, yeah, And also for on-sentence common future, we implement the algorithm in-house, and then it has a lot of room to be optimized further. Yes.
So it's a lot less than running like a cloud or just like a regular computer.
Regular computer, yeah.
Okay, thank you.
So my question is, your technique is successful in your application. I think I wanted to ask, do you think the reason of the success of your technology is because of the problem, or do you think your the technology can apply to other applications? Maybe do not have concept of drifting in the text box?
Yes. So, like I mentioned here, in legal domain, in predictive coding specifically, here are the reasons for concept drift. But concept drift, especially for text data, it could be, there's a lot of scenario where you have this problem. For example, spam email data, like I mentioned a little bit. These are text data, and it's constantly changing. So I think actually a lot of streaming text data has this problem. I was talking to a friend who works for a media company. They're trying to categorize the topic of the news or category of the news. So Donald Trump in 2008 or 2009 will be, the news about him will be very different from the news about today or even next month. So these are all online learning problem where your data pattern are constantly changing.
So any intuitive explanation?
So yes, so the intuitive explanation is because I think the technique we used is specifically like modeled for this time varying problem. Yes.
Thank you.
Thank you.
Thank you.